So good afternoon, everyone. Today is the second day of Claudio's mini course. He sent me his notes with some corrections on section 2, which he will be speaking today, and I will send them right away in the WhatsApp group we are using to communicate. Okay. And meanwhile, Claudio, you can start. Let me just recall that last time I interrupted you. You were going to present one last example.
Yeah.
I don't know if you want to.
Yeah, I will.
Okay. Thank you, Claudio.
Thanks. So, right. Today I would like to say a few words about the classification of symmetric spaces. Of course, this is a technical argument, and I cannot go through every detail, but I want to give some ideas. And so, last time we were talking about this linearization of symmetric space. So if M is a symmetric Riemannian symmetric space, let me recall then how to linearize it, right? So we know M is homogeneous, so we can write it as a homogeneous space. So G, say, is the full group of isometries here. K is the isotropy group at the base point, and then we have the geodesic symmetry, right? At the base point, which is the geodesic reflections, it's an isometry. And we can take conjugation by this. So, well, this is an isometry, so it belongs to G, and we can take this automorphism of the Lie algebra. And it's an involution because the geodesic symmetry has order 2, right? So, yeah, it's the identity. And therefore, we can take the K and P plus minus 1 eigenspaces of S, right? And so it's easy to check that K is going to be exactly the Lie algebra of the isotropy group, and P can be identified with the tangent space at the base point, right? And moreover, we can say that this, this K is a compact Lie group because it's an isotropy group, right? And in fact, this K preserves the linear isotropy representation of K on the tangent space. It preserves the inner product here. So we have, we can lift under this isomorphism here, we can lift the inner product on this tangent space to add K invariant inner product. Euclidean, it's an Euclidean, right? Inner product on P. And that's what we get. We get this triple, which we call orthogonal involutive Lie algebra. or we can abbreviate also oil algebra. So orthogonal refers to the existence of B, right, involutive, because we have this involution. So this is what we call involutive decomposition. Of G. So it means that, well, K is a subalgebra, K bracket K lies in K. We have the action of K on P. And more important, most is this property that P bracket P is contained in K. So this comes out of the science rule, the rule of science, right, for the eigenvalues of S. Okay, so I was going to give one example more. So this example, if H is a compact connected Lie group, then in the last lecture we already saw how to introduce to view H as a symmetric space. So the geodesic symmetry at the identity is an inversion map, right? So here H is equipped with a bi-invariant Riemannian metric. And then it's a symmetric space, and geodesic reflection at the identity is inversion map in the group. It's a homogeneous space and so on. What about the orthogonal involutive Lie algebra? Okay, well, here the isometry group of H, at least the connected component, it's known to be isomorphic to H cross H, where the first factor acts by left translations and the second one by right translations. And if we, so this is going to be our, well, yeah. So the Lie algebra is H plus H, and the isotopy group well, yeah, here in the notation I was using, this would be G0 in fact, right? Identity component, and then the isotopy group here is well, yeah, well, maybe yeah, I can say that it's just the diagonal, right? Because we take the base point to be the identity here. Then if we act on the identity by left and right translation with the inverse, then this is going to be 1 if and only if H1 is equal to H2. So that's the diagonal exactly. And therefore, the Lie algebra is the diagonal here also. And what about the involution in this case? Well, the involution must be what's going on? Transposing the coordinates. This, so the fixed point set is exactly the diagonal, and P is the anti-diagonal, right? X minus X. Okay. And right. So yeah. Well, yeah. The metric is a multiple. Well, it's a bivariant metric. I mean, it could be a multiple of the Carter-Killing form, or depending on how many simple factors H has. So, but this is not very important then. Okay. Right. So this is one example. And so what about the classification now? So the idea is to classify such triples, such oil algebras, right? So the first thing okay, yeah. Let me give one definition first. We say this oil algebra is Euclidean if P bracket P is 0, and it is irreducible if the add K action on P is irreducible. Okay. So the Euclidean oil algebras, they correspond to Euclidean spaces, in fact, or quotients, or Euclidean space, like tori, flat tori. And this is not difficult to see. Because, well, yeah, maybe I can show this. If this is Euclidean, suppose this is Euclidean, then of course this is the definition. P of P is 0, right? So we write G as K plus P. This implies that this is a semi-direct sum, because K is a subalgebra, right? P is abelian, and K acts on P. So this Lie algebra is a semi-direct product of K with P, right? We can view P as a abelian Lie algebra. K is an abelian Lie algebra, and there's an action of K on P. Semi-direct product, we say, right? Yeah, semi-direct product. And well, yeah, the Lie algebra level is semi-direct sum. Maybe it doesn't matter. Yeah. Anyway, so let us put dimension of P. Then we can isometrically identify this with Rm, with the standard scalar product. And then, since K is acting on P, preserving B, we can, and the action is effective also. We can view this as a subalgebra of SON. Okay. So what we have in the end is G is like SON, semi-direct product here, some action here, I don't know. Anyway, some action on Rn. And, well, could be SON or could be something containing SON, yeah. Anyway. So, right, could be any, K can be any subalgebra SON, and the symmetric space G mod K is going to be isometric to, well, depends here. If it's simply connected, then it is Rn. Otherwise, could be some quotient also. Anyway. Yeah. And the irreducible, let's suppose now this is irreducible. Well, yeah, if this is irreducible, it means that the add K action on P has a unique invariant inner product up to scaling. Because if we have two inner products which are invariant under K, then we can diagonalize one with respect to the other, and the eigenspaces will be K-invariant subspaces. So if the action is irreducible, there can be only one eigenspace. So there are multiples, one of the other. Okay. With these remarks, I can just state now in the decomposition theorem so let GSB be an oil algebra. Then there is a decomposition of the Lie algebra G0 plus G1 plus GR, and this is a direct sum of ideals. Such that each GI is S invariant B this G0 is Euclidean. If present, of course. And C, the other ones are irreducible. Okay, I'm not going to prove this. It's not difficult. It's basically linear algebra using Jacobi identity. So the bottom line is that if we have a symmetric space and we associate an Euler algebra and decompose like this, then if the symmetric space is simply connected, then it will have a corresponding decomposition into an Euclidean space and a product of irreducible symmetric spaces. Okay? And each irreducible symmetric space will have a unique invariant Riemann metric up to scaling. Each irreducible factor. And now we can give two more definitions. We can say that we can call so let's say this is well, let's assume, suppose this is irreducible. We say GSB is of compact type respectively, non-compact type. If the killing form is negative definite. So we write G as K plus P, right? It's negative definite on P. Respectively, positive definite. So, in fact, I should say also that this, in the irreducible case, these GI are semi-simple. And right. So in fact, the killing form and B will be proportional in this case, according to in the irreducible case, according to this remark here. Okay, now it's important to mention it's important to mention Cartan duality. So if we start with an oil algebra like this, the dual is another oil algebra. What we do, we complexify G, and then G star is going to be, so if here we have G is written as K plus P, and G star is going to be K plus square root of minus 1P. So it's easy to see that this is going to be a Lisa algebra, a real Lisa algebra of the complexification. And it's an involutive decomposition also. And we just transfer B to G star like this, define B star to be well, I should put maybe better to write like this. So it's, I think the best thing to do now is to give some examples to see what's going on here. So I'm going to do that. Let me just go back to the decomposition theorem. So we have, for an arbitrary oil algebra, we can decompose it into an Euclidean summed and Euclidean component, and then these irreducible components, some of compact type, others of non-compact type. So the classification is reduced to understanding irreducible oil algebras. So let me state the result then and give examples. So the irreducible oil algebras fall into 4 disjoint classes. Let's say class 1, 2, 3, and 4. Okay, so class 2 are compactly groups, say compact connected groups. We have already discussed this, right? And class 1, well, yeah, so I should say in terms of oil algebras, right? Yeah. So class 2 is, so what we, the first example we gave today, where H is compact, simple, and S interchanges. Components, yeah. Right. So here, B is a multiple of the killing form. Let's say beta is a killing form, okay? and this multiple is negative in this case. So class 1 is, we have G is also compact simple, and S is an involution. And here also beta is lambda. B is lambda beta with lambda negative. So this is class 1. Class 3, so 1 and 2 are compact type, okay? These two are compact type. And now we have non-compact type here. And Cartan duality interchanges. One with 3 and 2 with 4, okay? So what's 3? 3 is, so G is a non-compact, simple Lie algebra. With complexification simple. So G is not a complex Lie algebra in this case. And K is a maximal compact subalgebra. And it will be automatically compactly embedded also. And in this case, B is a positive multiple, the Killing form. In class 4, G is the realification of a complex Lie algebra. And K is a real form, also a maximal compact subalgebra. It's a compact real form, right? Yeah. So here also the multiple is positive. So these are the 4 classes. Let me give you a few examples. Okay, so especially class yeah. So let's class 1, for instance. Take G to be SUN. So these are skew Hermitian matrices of trace 0, right? Very standard involution is just conjugation. This is the same as, because Q Hermitian means X plus transpose conjugate is 0, right? So this involution is a linear map over R, right? It's an automorphism. And the fixed point set consists of matrices. What's that? So we want X to be equal to X bar, right? So real matrices in G. Therefore, we get SOM here. Skew symmetric matrices. What about P? So P, so these are real matrices. Now we all the real matrices in SUN. So P will be the pure imaginary matrices. So where X is real, right? Something like that. So we want this is, I'm writing usually, I think, square root of -1 here. So we want this to be SUN. It means that we take transpose conjugate. This is minus X, right? Minus this matrix, yeah. So therefore, X is real. And therefore, this shows that X must be symmetric. So the involutive decomposition in this case, G is equal to K plus P. It's like this. SUN is SON plus square root of -1 times symmetric matrices of trace 0 n by m, real. This is involutive decomposition. And this is under S. And this is class 1 because it comes from involutive decomposition of a compact simple algebra, right? And now we take Cartan dual of this. The Cartan dual of this will be, it's easy, SUN will be, well, we don't know what it is, but in principle, so G star will be, so we just cancel this square root of -1, right? And therefore, we have here skew symmetric matrices, and here we have symmetric matrices, trace 0. So if we add skew symmetric matrices to symmetric matrices, we get all trace 0 matrices. So we get SL and R. So that's the Cartan dual. The symmetric space, so this is class 3 now. So the symmetric space here is SL and R over SON. And here it was SUN over SON. This space can be seen yeah. Yeah, this can be seen as the space of positive definite symmetric matrices. Just by thinking in terms of Gram-Schmidt autonormalization process.
With determinant 1, right?
Yeah, right. Yeah, you're right. Determinant 1, yeah. yeah, we would take something like this, right? This one would be so there's an Euclidean line here, Euclidean factor compared to this one. Yeah. Okay. Right. Scatter duality and yeah. See, using Carter duality, it suffices to classify. Well, class 2 is already classified because this corresponds to the Killing-Cartan classification of compact connected Lie groups, right? Simple Lie groups. So the classification, using Cartan duality, the classification amounts to classifying now class 1, which means involutions of compact simple Lie algebras, right? And this can be done. In fact, I wrote most of the argument in the notes. I skipped just some very technical points. But another way would be to, instead of classifying class 1, classifying class 3 also. So irreducible symmetric spaces in class 3 are in bijection with real non-compact simple Lie algebras. It turns out for each given real non-compact simple Lie algebra, there's exactly one, up to conjugation, there's one involution with fixed point set and maximal compact subalgebra. So this so-called Cartan decomposition of G. So this is important. Let me write this down. Given a real non-compact simple Lie algebra G, I can write like this also. There's a unique maximal compactly embedded subalgebra K, and well, up to conjugation. And well, I can say just maximal compact, it will be automatically compactly embedded, meaning that the adjoint action of K on G preserves linear product. And K is the fixed point set of an involution. S of G. So we can write this involutive decomposition under S. And therefore, we have an oil algebra and a symmetric space associated to it. And it's unique because this case and S, they are unique up to conjugation. So this is also called Cartan decomposition. Of G. So one example, let me give you one example quickly. So say we take G to be SO P comma Q. So special orthogonal group with respect to this indefinite inner product. This is a non-compact Lie algebra. And right. Well, the associated symmetric space is this indefinite Grassmannian. And the Cartan dual, so let's say, yeah, the Cartan dual is this compact Grassmannian manifold. Right. So what happens here is that for this Lie group, I mean, we can write like this: SON, where n is P plus Q. We have a family of involutions, conjugation by this matrix. IPQ is identity minus identity. Block form like this. So for this compact Lie group or the algebra, we have this family of involutions, right? But if we consider the non-compact duals, you get different non-compact Lie algebras for each PQ, pair PQ, right? So either you fix a compact simple Lie algebra and then you vary the involution, or if you go to the non-compact side, then you are changing the Lie algebra, and then you have a unique involution for each one of them. Okay. Well, I have 10 minutes more only, and I'd like to talk about restricted rules. So here, now we see that we can either start with an oil algebra in class 3 or 4, say G simple, right? Irreducible, or this irreducible. And then G is simple here. Or we can start with G, real, simple, non-compact. The algebra is equivalent, right? It's different points of view, but we get essentially the same set of objects. Yeah. And then there's this idea of restricted root decomposition of G. How do we do that? So, well, we have this Cartan decomposition, K plus P. And then here we take a maximal abelian subalgebra. Sometimes this is called the Cartan subspace. Well, we know that this is an involutive decomposition, so P bracket P is containing K. So any subalgebra of P must be abelian, therefore, right? You take a maximal abelian subalgebra then. And so what we want to do is to consider the adjoint action of elements of A on G. And simultaneously diagonalize, okay? So we have to check that the elements of A under the adjoint representation are diagonalizable. They act as semi-simple endomorphisms, right? So one way to do that, we define this Euclidean inner product Euclidean inner product on G. So what we're doing is very simple. I mean, the killing form is negative definite on K and positive definite on P. So we just change the sign here to make it positive definite everywhere. And then with this inner product, we can easily see that at H, for H in A, this is self-adjoint or symmetric with respect to this inner product for any element of A. And this is abelian. So we can, we have a commuting family of semi-simple endomorphisms of G. So we can diagonalize. We can write G as G0 plus. So this is the zero eigenspace, and these are the other. So we have decomposition like this. Let me explain this better. So G lambda is the eigenspace. So elements of G where at H acting on X have this eigenvalue. Okay. And G0 is the centralizer of A. in G. But A is contained in P. So the centralizer, so A is S invariant. So the centralizer will be also S invariant. So it will be the centralizer in K plus the centralizer in P. So this we call, say, M. And this is going to be A because A is maximal abelian in P. So this is M plus A. Okay. And delta GA, this is the set of restricted roots. It's a finite set. And it gives an abstract, it gives a non-reduced, root system. On A. And what else? We have, in particular, we have this kind of bracket relation, right? And it is to check also that S maps G lambda to G minus lambda. Okay. So from here, we can get the Wasawa decomposition, for instance. K plus A plus N, where N is nilpotent sum of the, well, we need, to introduce some notion of positivity, right? And then we have this nilpotent Lie algebra, and well,
Claudio, you have 2 more minutes before
2 more
questions.
minutes. Yeah, I'm going to finish. Let me finish and just relate these restricted roots with K plus P. So because of this, G lambda plus G is S invariant. So therefore, we can write it as K lambda plus P lambda. There's a K part and P part. It turns out it's easy to, this is linear algebra. This Kp are going to be the elements of K lambda, so are elements in K such that at H square of X. And similarly for P. Well, right. This is important to do geometric calculations, this K lambda and P lambda. So to finish, I have a few seconds left. So K is going to be M plus the sum of K lambdas. Now lambda, just take the positive ones. And P is going to be A plus the sum of the P lambdas. Right, and there are more properties you can check in the notes. And I think I'm going to stop now. Yeah.
Okay, thank you, Claudio. I have some questions, but first let's see if anyone has. Well, I will start the question. Claudio, I have two questions.
Sure.
One is just a curiosity. This kind of the cartoon duality does it have anything to do with Weil's unitary trick?
I don't think so. Let me see. Weil's unitary trick is what? It's just a complexification fact, right? If you have
It's also compactification.
sorry?
I have studied both, but I don't recall the details. But it's
Yeah, I
it's
think
also
duality,
going from
duality was introduced by Cartan himself, if I'm not mistaken.
because why
Yeah.
unitary tricks you go from a complex like GL and C.
Yeah, you find the compact
to
real form. Yeah. You find the compact real form. This is yeah. The existence of compact real form was proved by Cartan first, case by case, and then later Hermann Weyl gave a general proof. And in fact, I
so
think
maybe that's
Weyl announced it had a general proof. He didn't. It was just an announcement, and the Cartan saw the announcement, and then he realized he could also prove this. So he proved this, and then Weyl proved independently of Weyl. So this is more or less the story, I think. But Weyl, of course, used this because for compactly groups, there was this idea of invariant integration, and this was very powerful, right? To prove,
representation theoretic stuff.
yeah, right, like complete reducibility, right, and so on, right? Yeah,
Okay.
but I don't think I don't see direct connection with Cartan duality. I mean, of course, I mean, you have class 4 here, which depends on the existence of a compact real form somehow, but yeah.
Yeah, I don't know, just came to my mind. The other question is about something I read in your notes. I found it interesting because you are classifying like the infinitesimal part, right? And another ingredient is the covering space.
Is what?
So there is the studying coverings of symmetric space. Yeah, it's further ingredients for the classification, and
Study what? Sorry.
the covering.
Covering. Oh yeah, right. Yeah.
And the I had studied that already, but the place where you take the pi one wasn't very clear to me. And I saw in your notes that somehow this is related to the transaction group, the centralizer of the transaction group. I found it very nice because I hadn't seen such a concrete presentation. So it was always an abstract presentation of the fundamental group.
Yeah. And of course, the fundamental group is abelian, right? You. Yeah. Or symmetric space. Yeah. Well, yeah. That argument is from Joe Wolf's book, right? But it's only half of the argument is there. The other half is more technical. Yeah. So.
Okay. I had some Borel notes where it's not. It's incredibly. As you said in the first lecture, Borel notes is very clear. You read and then you understand what. Now I understand. No, he understood. You're just using his power. But that part was kind of abstract to me, where the fundamental group lives, and in your notes, this is very clear. It is related to the transactions.
Yeah.
Yeah, in the next lecture, I saw your notes were divided in lecture 1, 2, 3.
Right.
And I don't know if it's a coincidence that you have 3 days of lecture here.
No, it's not a coincidence. You told me there would be 3
that's very nice.
lectures. So I had already some material, and I kind of adapted it to these 3 parts.
Okay.
Yeah.
So the last lecture
Will be about geometry. Yeah. So we haven't computed the curvature yet, right? We need to compute the curvature of symmetric spaces and talk about flats and rank and
nice.
total geodesic submanifolds, maybe cut locks, conjugate locks. That's a lot of. There are many things. Yeah.
Yeah, nice.
Yeah.
So it's tomorrow, right?
Yeah.
So the first day I got it wrong.
Yeah.
Carolina wants to ask.
Oh yeah,
Carolina,
sure.
just open your mic and.
Hello, Claudio, again. um, well, it's a general question.
Sure.
What happens when the group is simple, the isotropy subgroup is non-compact, and the representation is reducible? Do you know
You're talking.
how is the geometry of how is that symmetric space?
You mentioned the isotropy group is not compact. Is non-compact.
Non-compact.
So you're talking about pseudo-Riemannian symmetric spaces, right? Yeah.
Complex in general can be complex.
Pseudo-Riemannian, right? Yeah. There's a Durand. Well, I'm not very familiar with the theory of pseudo-Riemannian symmetric spaces, but I know that first of all there is a Durand decomposition theorem for pseudo-Riemannian manifolds, which is due to Wu, Chinese mathematician working in the United States.
Okay.
And specifically, this is a Durand decomposition theorem for pseudo-Riemannian manifolds, not necessarily symmetric spaces. And for pseudo-Riemannian symmetric spaces, there's a classification too. This was done by Marcel Berger, the 55, I think, more or less. And there are many papers about pseudo-Riemannian symmetric spaces.
I have the question is about the metric in this space, because the metric maybe is not be invariant.
Yeah, if it's not irreducible, then it doesn't matter the signature of the metric in this. It doesn't matter the signature. You need to consider the components, the irreducible components of the isotropy representation. And then on each component, it's unique up to scaling. It doesn't matter the signature of the metric. This argument works also in the pseudo-Riemannian case.
And the connection, the affine connection, maybe always can be related with a metric, or no.
The connection, the Levi-Civita connection is the same. I mean, for pseudo-Riemannian manifolds, there's unique
Okay.
connection, which is
Yes.
compatible with the metric and has zero torsion.
Mhm.
There is no change. Everything works. Doesn't matter the signature of the metric here.
Okay. Thank you.
The signature only changes the compactness, right?
Yeah. Yeah. Right. But what can happen in the pseudo-Riemannian case is that I think the result representation can be reducible, but maybe the restriction of the metric to the components is not non-degenerate. I mean, it is degenerate. This can happen, I think.
I see.
So there is this. This is a complication, maybe.
Okay, anyone has further questions? So let's thank Claudio again. Valeu, Claudio. Thank you.
Obrigado.